We'll also have a few algorithms which will look into that, and then I'll just show how you can carry out that in QGIS. So just a tools introductions which I'll be doing, but not physical demonstrations. So let's say this lecture is basically deals with theoretical network analysis part. So let's say that what exactly is the meaning of network analysis. So before that, we have to know that in any kind of navigation systems, we look for a few services, and we are also interested in few location-based services. So services, basically, we are interested in so services, basically, we are interested in finding out the different display maps around it. So that's the conventional way of doing things. Like whenever we carry out any, or initially we'll be having a kind of tourist guide maps and so on. So those are the standard maps which can be a part of it. Then there are also a few services like just get what is the shortest distance between two locations. We want to find it out, and then we are also interested in finding out few routes. So these are basically the services where we provide 2 points, starting one and starting an endpoint, and based on that we get a detailed routes and so on. So these services can be is related to a navigation systems which provides the detailed route plan. Along with that, there is also a need to have a location-based services, which is currently being used. That's basically location-based services like how to use the geocoders, where we will be giving the different states, then different street, or any kind of addresses, and that will get converted into latitude and longitude. So it's basically a conversion of a geocoding process. Similarly, the reverse is also there. So which is a location-based services, which is a required component for providing the navigation systems. Then we have additional need to have a different directory. So it means basically you need to look for a kind of directory structures, which we can think of basically is finding out what is in the surrounding areas. So there are different information within a specific range, and you want to find it out. Now this query is always will be executed during the runtime. So it's not that you'll be deciding at the starting an endpoint in GUI, but rather than wherever you'll go at that time, or that locations, any GPS location is being found out, and based on that, these directory searches and the routes are also being computed. So navigation systems requires these two, or under the navigation systems, these two important components are there. So in all these navigation systems are basically links to your network. So let's see that what exactly is the network. So by default, we can say the networks is nothing but a connected edge and point. So it means like we'll be having few edges and points. Then in case of navigation systems, which we also have a planar and non-planar networks. Then we are also having a directed and undirected networks. So planar and non-planar network means basically the network where we'll be having different edges. So those edges will be consist of different line segments, and the node points, which may be in junctions or crossing points and so on. So in the case of planar, you will be having all these line and points to be falling on a same plane. Where in case of non-planar networks, what happens is that these network lines may go from on the top of the others without sharing any junction points. So these are the cases where we have, let's say, flyover and so. So whenever we want to do any kind of computations based on flyover needs to be also taken into considerations, then we carry out those analysis under the non-planar networks. Then when we say the directed and undirected networks, so undirected and directed networks are that you'll be having a one-way route, or there can be navigations where in the bidirectional navigation is also allowed. So those kind of edges or a network in which these kind of directions, that how the route can be followed, if it is there, then we'll be saying the directed networks. If it is the direction is not part of any edges or any nodes, then in that case we will say it's an undirected network. So the few example of that is that road networks, there's utility networks, then usage network like the transportation and utility network has been widely used in the different transport and utility networks under that. So in all these networks, generally the basic objective is to finding out the optimum cost-based route. That's what is the most basic exercise. But apart from that, there may be we may be interested in finding out the service areas within a certain times or locations which can be covered and so on. So generally in the network analysis, we deal with finding the optimum travel route paths. So that's you just provided directions, and based on that we can get the output. So network analysis basically provides you those tools. So these travel routes may be from one point to another point, or maybe between all the points and so on. Then in some cases, we may be also interested in finding out the vulnerability in your network. So it means you may be interested in finding out that what will happen if one particular link goes off, or if any node is not having an accessibility to other parts. So what are those bottlenecks? So that's basically comes under the study of network partitioning. That's also a part of network analysis. Then finding closest facilities, which requires that from a specific locations, you want to find out the nearest another location. For example, if you're sitting at one place, and if you're interested to finding out nearby restaurants and so on, then those are basically a closest facilities. So closest facilities can also be linked to service facilities, like or the catchment area facilities can also be we can build on the basis of that. Then we are having a traveling salesman problem, which is again a modified routing problems. So in this case, you'll be having a few destinations. There is specific stop time, start time, and there is a requirement to have a route plan in such a way that there will be few stopover in between some places. So if the route is being found on the basis of that, then those comes under the traveling salesman's problems under the studies. So let's see that how it's being used in different GIS domain. So vehicle routing, different routing with stops, traffic, closest facilities, resource allocations. That's another area of basically the network analysis outcomes. So in this case, basically you'll be having one center of service facilities, and how you can connect to a multiple consumers to that services. So those are basically the resource allocation. So that basically helps us in finding out the number of people who can be served, or the area of territory or territorial area of services by a specific facilities and so on. So those are basically called resource allocation or location allocation problems. Then we can also have a service area in terms of time, distance, and so on. So monochrome is just an example of that, where given a specific time period on a path or from a particular place, you may be interested to find out that what are the different places which can be reached within 15 minutes or 20 minutes and so on. So those kind of things can fall under the service area network based on the service area facilities, where the cost can be based on the time. Then there may be another multiple cost metric associations. It means like you can provide if you travel from multiple places, or if you do a flight, basically you're bringing or taking the flight from one place to the another place. So in that case, what is the cost associated in the multiple routes? So that can be used for finding out the logistic cost and so on. So these are the basic broader area of network analysis, especially in the transport domain. So to carry out all these activities, the basic need is that you need to have a transportation network. So it means there has to have some kind of geospatial data sets. These data sets will include the different lines or the different routes. Along with that, you also need to have the services which you want to connect to these networks. So like in this example, what we're seeing, there are different streets are there, and with that streets, you'll be having a few bus stop, another rail line networks, which is again is being provided, the different rail stations which is available to us. So all these will be available as a separate layer in any kind of GIS data sets. So what we need to do is we need to create a kind of network data sets. So under that, what we do is we take all these different multiple features, that is basically those features existing in a single layer, or it may be a part of different layers. You take an input of you consider all of them as a single input, and those single input then gets converted into a network data sets. So network data sets generally consist of basically in terms of network data structures. So there are multiple ways of storing or in the network data structure, but basic concept in all of them is that you'll be considering all the features in terms of edge node. That's the basic concept which is being put in. So generally, whenever we carry out any kind of GIS analysis, so these network data sets is getting stored in different geodatabases. So like if you are using any commercial software like ArcGIS, so it provides you facilities where your data set is if your data set is having an connectivities where your or any kind of connections is available in your data sets. So all those gets converted into node, and finally you get a network data set. That's what is being provided by the software like ISRO, where tool itself is existing. But in some other cases, what you have to do, you have to make sure that whatever the network which you are building, or which network data set which you are building, each of those features are actually connected to your individual road segment. So most of the time, let's say if I want to carry out the analysis in using a QGIS, then in those cases, it is expected that your data set is topologically correct. If any path is there with the direction, so that the directions should be made available. All the different features like road, network, lines, and so on. So all those needs to have a particular node point connectivity with a specific network. Those things has to be ensured in a data set. Generally, in the open source software, we deal with open data formats or formats like basically the shape files, and also we have to make sure that the connectivity, no dangling points, proper connectivity between different features are actually existing in your shape files. And then later on, we can use that that output for generation of the different network analysis outcomes. So in all these, basically, we need to create modeling network data sets. So generally, in your network data set, you should have a few attribute data. So like we have seen, there are a few services. For example, you may not be knowing the lat long values, but you may be knowing the addresses. So it means like it needs to have some kind of attribute values associated with the information which is being queried, and that has to be, and then it also needs to have some kind of connectivity and other relationship with the lat long values and so. So so all those attribute data has to be there. So those attribute data actually can think of that each line segment or the node, if any additional information like what is the capacity of a particular road, what is the weight, what is the average travel time from one place to another places, and so on. Similarly, you can also have an attributes data informations available in different node junctions. So those node junctions may be the places where is the U-turn is allowed or not allowed. So all those actually is being required as a part of your attribute data. And then there's spatial information. So you need to have exact location of each of those individual points and connectivity between them. Along with that, whenever we carry out any kind of network analysis, we need to have certain metrics which is being used in network analysis. So like the length, the kind of direction, connectivity in case of the historical patterns, that may also will be required. So these are the basic data set which is required to be present in your network data sets. But nowadays, whenever we're talking about the different transport networks, then apart from these network characteristic, we also need to have some additional informations which has to be updated in a real time. For example, if there is any in between, if there is let's say if the road network is there, and within the road network, a certain segment is not accessible, so that impedance cost should also be present, also should be provided to us. Along with that, sometimes we may be interested in finding out the vulnerability of your networks. So in that case, we need to know what kind of network connectivity is there, is the network is having a specific bottleneck, and so on. So those are like different kind of patterns which is existing in your networks. That also has to be there. And sometimes what may happen is that during the execution, or whenever you are running, or the network characteristic itself may change it during the runtime. For example, there may be a center of movement. So during the work hours, people may move or avoid that junctions, but during the holidays and so on, people may go to the central markets and so on. So that kind of the patterns or the connectivity, the way we or the corresponding different characteristic may change during the runtime. Along with that, we also can create multiple hierarchies within the networks. So we can say that if the network is having levels like tertiary road, primary road, state highways, and so on. If you're having those characteristics, so that can also be built in and can be used for finding out the different outcome of network analysis. So so when you have this information, this has to be arranged in a form of appropriate way. So there are ways to do that. One is or any kind of network problems generally will have a kind of conceptual models. So those are nothing but building all those informations at the conceptual level itself. Generally, the entity relationship diagram is being used, and we also use the mathematical models like graphs for doing that. Then we are having logical data models. So those logical data models are nothing but providing the connectivities, node, and the different features. Like if you want to add or subtract, those kind of logical models has to be there. So generally, it's being built using a few libraries, network based libraries, or it can also be based on a few SQL statements that can also be created. And finally, when we want to carry out these, then gets implemented into our storage structures. So you'll be storing it in a form of matrix, or it may be a linked list and so on. So that kind of physical storage data models. And on the top of that, the corresponding algorithms or executions take place. So let's have a look of the what kind of different network metrics which is needs to be present for carrying out the network analysis. Those metrics are like the continuity, topographic space, and spatial cohesion, or the connectivity. So these are the specific measures when you are interested in finding out the extended part of your network analysis. So if you're having just information of the network length and node and characteristic, then you can find out the cost-based and outcome, like what is the route, shortest path in case of impedance, something like that. But if you want to do vulnerability analysis, in those cases, we need certain other parameters. Or if you are if you want to find out the overall from the planning perspective, then these additional metrics like continuity, topographic, spatial space, how the topography is there, that has to be taken into consideration while solving the networks, along with the spatial cohesion and connectivity. Those are the things which can help us to find out the carry out, like if else, or if somebody tells us that we have to reroute the whole or replan the whole road network in such a way that the overall fuel consumption should come down and so on. So if you want to carry out those exercises, then these metrics may help in. A few of the measures like there's another measures which we call it as absolute distance and relative distance. This is the important concepts. So basically, the absolute distance says that the direct latitude and longitude based distance that can be based on the edge, weighted edge. But if I want to consider the factors like continuity, topography, and so on, then that's called a relative distances. So it's like the simplest example of that is the time base. So there may be a route which may be 1 kilometer, but in the time domain, to reach from 1 kilometer distance, we may need to spend around 30 minutes. Or there may be another route which is, let's say, 5 kilometers, but that can be traveled. There might be another path from the one place to the another place. In that case, the 15 minutes that can be, we can travel it 15 minutes, even though the length is 5 kilometers. So those are actually called relative distances. So those relative distances are again built in using these cost metrics into consideration, along with the type of networks, how it's being used, and their connectivity, the capacity of the different nodes, and so on. So you see that there are very large areas of further network analysis. And network analysis is not restricted to only finding out the routes, but rather than vulnerability, accessibility, and so on can also be studied. So if you're interested in road networks, so generally we get we can get it using the OSM maps. OpenStreetMaps can be one of the starting points of the road networks, but those data sets, the OSM maps cannot be directly used in your GIS applications. you need to do some kind of pre-processing on the top of that. So those pre-processing are like removing diagonal points. In some cases, you can also use few libraries which can help you in cleaning and providing you the proper topological relationship or hierarchical relationship built in your data sets. Then you can also get an air traffic open flight air traffic data sets that can also be used for network analysis. And there are a lot of other web services which can also provide you the network data sets which you may need it. So let's say that in the if you need to have kind of representation of your network, in that case, how can we build it from the road data sets? So if you take a road data set in this example, so where we are having a roads, which is having a few, the name of the roads, and there each of those roads will have a few junction points, and each junction points can be considered as a node, and correspondingly those road segment or the junction point may also have additional attribute like is the turn is allowed or not allowed. So it means like if the turning is allowed. So this is separate from the edge level attributes, like if you're having a different segment, so road segment may have one way, two way, and so on. So that's one part which is related to a segment. But there's also another attributes which is related to each of those nodes. There, the additional information like the turn is allowed or not allowed, those kind of attributes can also be put in. So these are the important attributes which can be built for your node segments. So those are basically the conceptual kind of, so when we are having a relationship like this, so we know that the road segment, line segment, and so on are there. In terms of entity relationship approach, if you see, then this is the just an example, one of the examples where the roadmap may have a lot of those intersections. Those road intersection may consist of multiple segments, and then each segments will end up with a particular route, or it may be links to a node, or which may also may connect to another street. And for each of them may have a particular route with additional attribute like travel time and so on. So it's basically just gives an example that how you can represent the same road networks in a different entity relationship diagrams. So this becomes an important when you're using some kind of spatial data basis for querying and finding out or solving the different network analysis algorithms. Then to execute an algorithm, you need to have an understanding of graphical methods. Those graph methods are based on simple graphs. So generally, if you the graph is nothing but a kind of order pair consists of two sets. One is the set of all the vertices of the junctions, and second set is the edges. And this graph models can be represented in a multiple ways physically, but logically it simply means that you create each junction as a nodes, and there's a connectivity, and those connectivity with the directions can also be provided. So each direction connectivity is being represented as an edge. So this is just an example of a street which can be converted into a graph models. So these graph models are being used for carrying out the different kind of representations. So these graphs can be represented either in form of adjacency matrix. So adjacency matrix is a matrix-based representations where each of the connection is being put in as an entry in your matrix, or it can also be another physical representation in terms of linked list and so on. So if you're having if your network is having unidirectional graph, then in those cases you'll be having a single linked list traversal. But if you're having an undirected graph, then it's a kind of two-way traversal that should be possible. So basically, this example shows that whatever the the mathematical model of the graph is there, that can be represented in matrix form or in the form of linked lists. So once we have these representation of the network in form of graphs, then we can derive the multiple measures. So those measures are being used for another further analysis. So especially in the case of different transport analysis, these measures are important. So let's take an example. In this case, the measure one is called diameter. So it basically gives the longest, shortest path between any nodes. Like in this case, over here you see that this particular graph is being represented as this graph basically is represented in the matrix form as an adjacency matrix, and once you have that adjacency matrix available to you, then what you can do, you can create a diameter for the distances. Those diameter are nothing but the shortest path distances. So like what is the shortest path between node 1 to node 1? So it's basically a 1. So it's a 0. 1 to 2, you need to have a 1 path. Similarly, 2 to 1 will be a 1 path. Let's say, how can you reach from node 7? So I'll have from 1, so I can reach from first node, second node, and third node. So it means like first I'll be driving the first node, destination node, second node, and third node. So it means like there are 3 different segments which needs to be traversed. So the shortest distance between 1 and 3 is 1 and 7 is 3. So in case of diameter, whenever we want to find it out, all these shortest distances, it means all the shortest distance path between each node has to be computed. And then what we look for, that what is the maximum length or the shortest length which is possible. So in this case is the 4. So it means like if this length is available, so it means like the longest path or the longest node between in this network is reaching from path 2 to node 2 to node 7. So this requires 4 edges to be traversed. So in that case, the longest shortest path is basically a diameter. I'm again repeating, this is called longest, the longest distance which can be covered with a shortest path. So in that case, this is not the longest path though. Like if I want to make a route quite complicated, then in that case what we can do is we can traverse from 2 to 4, 4 to 6, 6 to 1 again. Then we can go to 3, 5, and 7. So this can be considered as the longest path, but the longest shortest path is go from 2 to 4, 4 to 6, 6 to 5, and 7. So this matrix is called a diameter. Similarly, we are having an detour indexes, which talks about that finding out the total distances between longest path. So all the total distances you compute along with the shortest path and so on. Then there are also other indexes like theta indexes, which says that if at any places you want to find out what's the average load in your network. So it means how many vehicles are on an average crossing through any junctions within a networks. So if you can partition your network and try to find it out, those metrics, then you can easily identify that these are the vulnerable areas or the risky areas where some impact or may happen on particular junctions. So this is called eta indexes. The eta indexes is just another matrix which takes all the path length and the number of nodes number of edges. So that's basically the average length between any two node if you want to find it out. So what you have to do is you have to take all the distances, sum it up, and then see what is the total number of distance. So those are called the eta distances. Then there's another very interesting matrix which is called pi index. So this pi index basically talks about or can be thought of as a metric for finding out the vulnerability in your network. So if you're having an shortest path which you're measuring, so like this is basically the total long distance, total distances divided by the average or the longest distance which is possible to reach. Like in this case, if I take this is a simple example where if I add all the distances in a graph, so there are total 8 different edges are there, and the longest path, longest shortest path in this case will have an edge of 2. So it means that there's an pi index of 4. In another case, if you see like in this case, so this is having some extra edges attached to us, and this may also leads to the smaller number of the diameter or diameter size, maybe length of the diameter size maybe a lesser one. So in that case, this will be having a slightly better pi indexes. So for the fully connected networks, the pi index is quite high, and so if your pi indexes is the larger, so you can call it that this networks is more sustainable. So it means like even if certain links are there, still there won't be much impact on it. So these are the few measures which is being computed once you're having those representation of your data set in form of networks. Once we have those metrics, we can also get the cost of metrics in the graph, which will be used as for solving the different routing problems. So generally, if you see that this is just an example that where your the minimum network or just a network which is sufficient to connect all the node will have an average path length quite high, where in case of fully connected network, your average length path will be low. So if you see that there will be a kind of your networks will be in general cases, we'll see that the networks will be somewhere in between. So based on this, we can identify and we can tell that what is the vulnerability of your networks and so on. So accordingly, vulnerability metrics can be found out. Then we can also use the weighted networks. Once we have these networks or the cost of different nodes available to us and different node and edges are available to us, then we can look for that to identify that we can compute the minimum spanning tree. So it's basically the shortest or the low cost distances which is possible to find and go from one place to the another place. Or in some cases, we may also be interested in finding out the basically the how the different networks are connected. So it's basically triangulated methods are applied, which helps us to identify is there any additional path or cost which is possible with the, or is there any other alternative route or minimum spanning tree can be constructed by adding an additional nodes and so on. So once we have such cost matrix associated with that, then we can create an alternative routes. This is just an example where in your networks, the direct connectivity is there, but the travel time may be dependent upon the height or the slope terrain and so on. So the corresponding impedance will go low, high in that case, or in the cases there may be impedance. In this case is the lesser, and if you go in there may be higher one. So these cost effect analysis can also be carried out or can be created with the help of which can be used as a cost matrix in the graph. Once these graphs are there, then we can compute the different paths that can be computed. So like in that case, each of the vertex and edges, depending upon it's an order or not orders, then the path can be considered as a sequence of vertices with a low cost, and that can be used. So we'll see a few examples of them to find out the complete path. So this is an example of undirected and directed graphs, where in this case, each edges you can traverse from any order, so you can reach from 5 to 4 or 4 to 5, where in directed graph, there is a limited movement only, and the movement is only in a single directions. So once you have these graphs, then what you can do, you can create different algorithms to find out certain metrics. So this is just an example of Prim's algorithms, which is nothing but finding out the minimum distances from one point to the another point. So you have a starting point, and from this point we are trying to find out what is the distances or the cost to reach from these points to the other nodes. So that's basically, you start it from the starting point, then you look for the next, based on the cost, you can select the nearest neighbors. So in this case, like this is the first node, this is the second nearest node. So you get this cost, and these two are now part of the new group. Now from these two group, again, we look for what is the next unreached node. So in this case, from the D, there are connectivity to E, but that cost is 4. From the D, again, you have another connectivity to a node C, which is cost of 2. So it means like I can drop this E, but nearest point is from D to C is, or the nearest distances in terms of cost is C. And from the B, it is A. So now out of these B and A, again, the total cost from this whole group is to A. So now what will happen is, in the next case, or the A will be now part of these groups. So this is basically starting with B, you are adding the D, and then out of these, all three candidates like A, C, E, you have selected the least cost node. So we are taking in this case A, so that creates a new group. Then from this new group, again, you start looking for the unreached other nodes. Like in this case, from A, the distances to the F is 3, A to C is again 3, and D to C is just a 2, and D to 4 is E. So in this case, if you see, once we reach this case like A, B, C, then out of all these candidates, F, E, C, the candidate which we are going to select is a C. So the C will get connected, and this will be now part of our the group. Similarly, we just look for the next level and so on. So this basically, the minimum spanning tree algorithms basically tries to find out the minimum cost from reaching from one node to the another, to the all the nodes. So this gives the kind of connectivity of whole graph. So let's think that how these things can be used in different applications. So if you remember, we had an location and allocation problems where we want to allocate different resources to a particular service center. So in that case, what may happen is that these minimum spanning tree for all the destinations or the consumers or the service beneficiary to whom we want to connect our service centers, we will start computing the Prim's algorithm for all of them as a separately, and then we will see that there is a group of clusters is being formed in such a way that the around the particular service center, the total connectivity cost to all the different service managers is least. So this is just an example where minimum spanning tree can be used to find out in case of service location and allocation, and apart from the finding out the shortest path from one locations to the other locations. In all these, basically the whenever we are creating these algorithms requires, and apart from those vertex and edges, the cost which has been created using the different weight matrix has to be considered. Then these algorithms can be used with other examples is like the Discus-Strauss algorithms. So it is also another example to find the shortest path. Then it's basically also called the greedy algorithms, where a single source shortest path based on the graph theory is being solved. Generally, in such algorithms, like in this case of Discus-Strauss algorithm, you provide an input G and V node, and based on the connectivity and path, we can find the cases. Just an example of the Discus-Strauss algorithm similar to the Prim's algorithms. The only difference is that distances has to be found from starting point to the end point. So in the Prim's algorithm, you have to reach to each of those nodes, where in case of Discus-Strauss algorithms, we can reach and we can stop as soon as basically again the partitioning is being done in such a way that there are individual nodes are there in at the end you traverse all the nodes. So this is just an example where different cost is being provided. So you start it from a node A, and then you look for the nearest distances. So the nearest distances you attach it, and those two nodes are now being covered. Out of those two candidate nodes, you select the node C, which is the least cost from the B and C. So you say that C has been reached. Then what you do is you look for another cost to all the candidates. So in this case, from the A to B is 10, C to D is again the cost is in this case is 4, 8, and 2. So in that case, 4, 8, and 2 is there. So in that case, reaching the cost from E via C is actually total cost is 5. So this is basically giving you the total cost. So that total cost is being provided, and that is again the least one compared to the previous case, and E is being attached. Then in the next level, again, we look for the costs from reaching from A to other places. In this case, it's like in this case, there's already a cost 3 is there. Then from this, if you want to reach to a B, so additional 4 will be needing, and you'll be having the total cost of reaching a B is 7. And then similarly from E to D is again 9. 5 plus 9 is, or similarly the other way around is 5 plus 9 is 14. And the least cost again via C is 3 plus 8, so 11. So out of those 14 and 11, we will select the D path. So D can also be D can also be considered. But out of these, this is the cost of reaching or taking the next node. 11 is reaching D. Similarly, the cost of reaching to B is from A is 7. So out of these two, this is minimum. So we'll just select the minimum of that. That is the B is being selected and it's being reached. And then finally we get a next node. So once we have all the from the source, if you're able to reach all the nodes, the algorithm starts. So if you want to carry out these analysis, so in the QGIS, you are having tools, especially not in the earlier tools, but recently now you're having these as a part of processing toolbox, which is called network analysis. So under that, you'll have a service area from layer, from point, a shortest path from layer to a point to layer, and point to point. So in this case, what happens is that in QGIS, you have to provide road networks, and you need to provide another layer from which is going to use that layer. So wherever we see a layer, so that layer is nothing but service area around the road networks. And whenever point is there, so that will be another information from which is going to use the network layer for finding out the different outcomes. So those are like service area. You start it from the point, and within the time frame, if you want to traverse from one point to another point, so that can be that can be solved using a service area from starting point from a distance. Similarly, you may be having multiple starting point within a particular distances. That is nothing but a layer. So it's like in first case where we say starting point from a service area from a point. So in this case, this tool basically is going to use just one from your one point to the another point, where in case of service layer, you have to provide all the input points from which you want to find the distances. In the shortest path, you can find out the shortest path between 2 points using the networks. That's basically 2 locations on the same networks, or you can have a starting point and you want to reach to the multiple points that can also be that can be found out using point to layer options of network analysis. And if you're having a multiple starting and multiple layer endpoints, then in those cases, layer to point options can be applied. So these PRIMS, Discustas, all those algorithms has been implemented in this QGIS toolbox to give you the shortest paths among the shortest path between the point and layers. So with this, I'll just end my session. So we'll take a few questions.